Annenberg Media.
Why can I see myself in the water?
Why can't I see around a corner?
Is all animals feet and color? Where do all the colors in the rainbow come from? Why is it windy sometimes?
What would happen if all the plants disappeared in the world?
Do plants have to be green?
Why are the days longer in the summer than the winter?
These are questions that are often asked in classrooms, and all of them can be linked by the phenomenon of light. I'm Anita Greenwood, a science educator at the University of Massachusetts Lowell. I work with elementary and secondary teachers, helping them to learn about how children think about science concepts and how to approach the teaching of science concepts.
And I'm Christine Jones, an astrophysicist here at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. I carry out research using X-ray observations, another form of light that we'll talk about later in the series. Welcome to Shedding Light on Science. In this series, we'll look at some of the activities that are commonly undertaken in elementary classrooms relating to light. We'll also go behind the activities and look at the science that these activities are designed to illustrate.
The explanations we'll give you are designed for teachers and not for students. The purpose of the series is to provide some of the background science content that may help you devise appropriate lessons. So Shedding Light on Science is a science content series rather than a series devoted to science teaching methods.
In the first 3 workshops, we'll describe some of the properties of light and also explore other forms of light that are not visible to the human eye. And then in the 4th workshop, we'll look at how the eye works.
In workshops 5 and 6, we'll learn how green plants convert light energy into chemical energy through photosynthesis. And we'll investigate how ecosystems function.
And then finally, in the last 2 workshops, we'll look at what causes seasonal changes on the Earth and what makes our wind and weather happen.
Now, obviously, we can't address all of this material in depth in 8 hours of videotape. So we've designed additional materials to assist you. You can access these materials in a variety of ways. Those of you who registered for this workshop series have already received the print materials. If you don't already have the print materials, you can retrieve them from our website. The website also contains additional information, activities, and discussion areas. Watch for web icons during the programs. They'll guide you to the appropriate section of our website. For instance, highlights will give you more information about the topic or suggest activities that you can try to deepen your understanding. Like links will provide you with the addresses of other websites for more information about a topic. The Shedding Light on Science web address is www.learner.org/channel/workshops/sheddinglight. You can also talk with your colleagues across the country on our email listserv, Channel Talk. The address is channel@learner.org. We look forward to hearing from you.
Light is a beautiful but also a complicated phenomenon. Over the centuries, some of the most brilliant scientific minds, including Alhazen, Isaac Newton, James Maxwell, Albert Einstein, and Richard Feynman, have struggled to understand what light is, and we're still learning about it. At colleges and universities, entire courses are taught on the physics of light. But since we can't address all of the details about light in the time we have together, we've selected only the most important. In today's workshop, we'll explore what light is, that light travels, how shadows are formed, how fast light travels, and we'll begin to look at how light helps us see.
Whenever we as teachers begin a new unit of work, it's important to gather the initial ideas that students bring to the classroom, and then to revisit these ideas as instruction progresses. So we're starting this series by having you gather your ideas about light. During the series, you should look back on your early ideas and make changes or raise questions on the website. We'll return to these ideas several times during the series. We suggest that you keep a notebook to record key points of interest to you. What are your thoughts about light? What are some things you know about how light behaves?
Light is like if you had a fire, like light would come out of the fire. It like makes things bright. Light is bright. You get light from power and oil. You can get light from a light bulb. You can get a light from the power plant. The wires that are from outside. The sun. The sun. It's a big ball of fire. The light just travels down to Earth. It's a hot ball, and sometimes they used to come here, but this one is different. It stays in the sky, and it's a hot ball, and it's really hot. Because if you go on it, you'll get really hot. It would be too cold without the sun. It would be really dark, and we wouldn't be able to see. And it would be also cold. It'll get dark. Everybody would crash into trees and say, ouch. Plants couldn't grow. Animals couldn't live. The world would be wicked dark. There'd be no plants. There'd pretty much be no animals. We'd die because the sun helps plants grow. And animals eat plants. We eat things that come from animals and animals. And if we don't eat that, then we don't have anything to really live off of.
So what is light? We know, based primarily on the work of 20th century scientists, that light is actually a stream of very small packets of energy called photons, traveling very fast. To help visualize some of the properties of light, we've set up a demonstration in which ball bearings represent photons. Of course, ball bearings are made of matter, and photons are really energy. But we can use the ball bearings to represent and help us think about some of the behavior of light. You'll see this representation used later in the series. So how do we know that light travels?
19, 20.
Oh, no, not again.
Have you ever seen children playing flashlight tag? Well, if you think about it, the light from the flashlight must travel from the flashlight to the person, if the person who is it is going to catch anyone. Here we see it. There's a light coming from the flashlight, and an object there is lighted.
Who's that? Oh, no.
The children playing flashlight tag begin to understand that light travels from a source, in this case their flashlight, to an object or another person. Although we'll talk in the next workshop about some ways to make light change direction, generally as light travels out from the source, it travels in straight lines until it strikes an object. Now let's look at a demonstration for another kind of evidence for how light travels. In this demonstration, we punch holes in 3 white cards. In the first card, there are 3 holes. In the second, 2 holes, and in the third, 1. We place the cards in a shallow water table and add a bit of powdered milk to the water in order to see the path of light. We then shine a light on the cards. Let's see what happens. The light continues to travel until it is blocked. So you can clearly see that the light travels in straight lines.
Another piece of evidence that light travels in straight lines until it strikes an object comes from studying shadows. We visited the Averill Elementary School in Lansing, Michigan, where Deb Smith from Michigan State University is working with Sharon Henriksen and her 2nd grade class. The children are trying to answer the question, what makes a shadow? Let's hear what they have to say about light and see some of their explorations of shadows.
I'm going to hold up is this box of crayons. And I'd like you to look at that and think about, can this make a shadow?
Everything that you can't see through can make a shadow. I think it will make a shadow because it would need some light and a little bit of shade.
How would the shade help it make a shadow?
Because if you don't get a little bit of shade and a little bit of sun, it will get mixed up and it won't make a shadow.
I think that it's going to make a dark shadow because the wood is really dark.
The one with the one hole at the top,
Mm-hmm.
it will make the same shape as the object is, and the hole at the top, it will the light will go through it, and the object, the light will go around it, and it will be dark, and that's how you make a shadow.
Why is there darkness here? Why is there darkness there?
Because there are no holes right there.
Because if the board, it might be a dark color. I mean, this might be light, and when you flash light on light, it gets dark.
When you flash light on light, it gets dark. What do you think about that, Cole?
I think that when you flash light on light, it gets dark also.
Is the shadow connected to the color of the object or to the object itself?
Well, maybe when the light hits the object, it turns black and then it reflects somewhere else And where there's holes, it reflects maybe white, the color of the flashlight.
Okay, so you have an idea that it's caused by some kind of reflections with the light.
Uh-huh.
So what's happening to make this dark right there?
It's painted brown
And why is this lighter?
because there's nothing in it.
Oh, you mean there's nothing in the duck?
Yeah, there's nothing in the duck.
Oh, okay.
No. If you go like that, it gets bigger. If you go like that, it gets skinnier.
You're right.
Better and skinnier. And when you put the flashlight far away, the shadow of the spoon gets smaller. I think that it gets bigger when you put it close because it has more light.
There it is!
So where's the light coming from to go through that hole? Where's it starting from?
There.
Okay, and then where is it going through the hole?
Yep.
And then where's it ending up?
And then right on the wall.
Oh, interesting. So why isn't there light here in the shadow?
Because I don't know.
Okay. Well, that could be an interesting idea to think about. Because you said light was going through here. Do you see my finger pointing where it's going through? Is the light going through here? Oh.
Because there's no holes right here.
There's no holes there.
And there's a hole right here that you can see through. This is cool. I just have to make sure. These not. It's getting very warm. It got a hole in it. And
Yeah, but
plus,
it disappeared when you put it over there.
I know.
I couldn't see the hole anymore.
Because the shade, it makes the shadow go away. Because I was like that.
Oh, why don't you get a hole when you turn it like that?
Because it's going that way. Look at the shade.
What's going that way?
Look at the shade makes it go away. Going back.
Where are we getting the light from?
The flashlight.
Yeah, so if you start right here, where the light is, and show me with your hand where that light goes to go around the cup. Where do you think it's going? Over the cup, and then where does it go after it goes over the cup?
It goes to the wall to show the shadow.
Ah, so how come none of that light goes right there?
Because there's no hole here. But if there was, there'd be light.
There'd be light in there.
Because the end here is blocking.
Oh, when you say blocking, what do you mean it's doing?
It's like holding the light inside of it. It stops it.
Oh, so it's almost like, if you were pouring water in the cup,
It holds
it would hold the cup. It would hold the
Just
water.
like
And
it's
you're
holding
saying
It's like holding the light.
holding the light. Oh, how
And
lovely.
then
What did you notice about what was moving?
the shadow was moving.
Yeah. Why
But
is
the
that?
crayon box is staying in one place. It's not
Yeah.
moving.
So why would the shadow move?
Because you're moving the flashlight. If you go one this way, it will go the opposite. If you go that way, it will go the other. It's been in
Oh,
one
how
place.
interesting. I don't think anybody else discovered that. Yeah.
It'll go over there.
Where is
Somewhere. It'll go over
Over
there.
there.
It's gonna be on their
let's
camera.
see.
The light shows because there's like no fingers part in there.
Okay.
There is no shadow in there. Yes, there is. There's a shadow right there. And the wall's blocking it. So that's kind of like proof. But when you put your hand there, you can see the shadow of your hand. Yeah, but so there might be not any wall by your hand, but on the book there is.
How come you're getting white in your shadow? Pink for me.
Oh, because the hole. Light goes through and hits that and makes the light show right there.
Okay, so if that were true, if the light is going through that light right there, could you stop that light from getting to the wall?
Yeah.
What could you do? What did you do?
I just put my hand over the backside.
You covered up the light, didn't you? All right, now you covered it right there. Can you cover it anywhere else and make it not go through? Aha. So
It'll
there's
show up
lots
on your
of places.
hand.
Yeah, it shows up. There's the hole on his hand. Ah, interesting.
If you move it very close, it kind of disappears, but it's still there.
When he puts his hand over it, you can't see any more of the light.
Is there light over there by the flashlight?
Yeah.
How do you know?
Because the light's shining right on her hand.
Okay. So where's the light starting from when it first comes out of the flashlight? Okay, so you think it starts around there?
Mm-hmm.
Do you think there could be any light over here in between? You want Alyssa to test it? Alyssa, see if you can put your hand, I'll hold this. See if you can put your hand in the middle here somewhere and see if there's light there. Oh. And so did your prediction work?
Yes.
It worked, didn't it?
The exploration of shadows in the primary grades is an important introduction to the idea that objects can stop the light, leaving an area with no light, the shadow. The Michigan children were constructing their own explanations of their observations. We heard ideas such as light shining on a light object makes dark, or a dark object will make a dark shadow. And most children recognize that although they cannot see the light traveling from a flashlight, they can put objects in its way that will block it. Shadow explorations in which children generate, test, and share their ideas provide them with wonderful opportunities for modeling what scientists do. In this demonstration, we are using the droplets of the spray paint to represent photons. When we spray an object, in this case a hand in a glove, with paint and then remove the object, we have an area on the surface below where no paint has landed. We can use this analogy to think about how shadows are formed when something opaque blocks the light's path. Now here's something for you to do. Here is a box with slits on each side and a light bulb inside. If this box is placed on the floor in the center of a dark room, and then the bulb inside the box is lit, what will you see? If the box with the lit bulb is placed on a table in the center of a dark room, what will you see now?
When we don't have the sun, clouds come instead of the sun. And then rain comes, and then first comes thunder, and then comes lightning.
Yeah, we get electricity from lightning, and sometimes when the lightning strikes, if it hits like the pole, the light will go out.
The sun gets to the earth because it's bright and it goes far.
When the sun changes, your shadow changes. If the sun is more direct or on top of you, the smaller your shadow is. There's a lot of different shapes to the shadow because there's a lot of different shapes on us.
A shadow follows you wherever you go.
As the light's on the ground, it like goes farther and it like gets bigger on the way it used to be. So it just like sort of like just runs but makes wider light on the ground.
When I look down on the ground, if I see my shadow's always taller than me. And that it like does whatever I do.
When a light hits a wall or the floor or something, it usually bounces off and keeps on bouncing off the stuff until it runs out of light.
We've seen some evidence that light travels in straight lines. But what do we know about how fast it travels? Well, when you think about it, it's obvious that light travels fast. When you turn on a light in a dark room, both the light bulb and the room seem instantaneously lit. Whether light travels instantaneously or has a measurable speed was a question explored in the 1600s.
In the 1600s, Galileo reputedly tried to measure the speed of light. He stood on a hilltop with a lantern, while his assistant stood on another hilltop with another lantern. The plan was that Galileo would open his lantern, and when his assistant saw the light, he would uncover his lantern. Then, Galileo would measure the time between when he first uncovered his lantern and when he saw the light from his assistant. But the speed of light is so fast, and the distance between Galileo and his assistant so relatively short, that they soon realized this experiment could only measure their reaction times and not the speed of light.
Longer distances or more sophisticated techniques would be required to determine if the speed of light were finite. Those measurements were to come in 1675. By that time, scientists knew how long it took Jupiter's bright moons to go around Jupiter. The Danish astronomer Olaus Rømer found that the moon Io disappeared behind Jupiter about 20 minutes later than expected, when the Earth was far from Jupiter in the Earth's orbit around the Sun, compared to the time when Io went behind Jupiter when the Earth was closest to Jupiter. So what was happening? Well, the orbital period of Io wasn't changing, but the distance from Jupiter to the Earth was. It was taking light from Jupiter's moon about 20 minutes longer to reach the Earth when the Earth was farther from Jupiter compared to when the Earth was nearer. With these measurements, Rømer computed the speed of light and showed for the first time that light does not travel instantaneously. With technology, improvements in measuring the speed of light were made in the 19th and 20th centuries. Today, the adopted value for the speed of light in a vacuum is 300,000 kilometers per second. Despite science fiction ideas about spaceships that travel faster than light, at warp speeds, physically it's impossible for anything to travel faster than light. But what do we know from our everyday experiences about how fast light travels? Think about a thunderstorm. First you see the lightning, and then you hear the thunder, although they actually occur at the same time. So we can use this thunderstorm observation as evidence that light travels much faster than sound. You may know that if you count the number of seconds between the lightning and the thunder, you can figure out how far away the lightning is. It takes sound about 3 seconds to travel 1 kilometer. Let's take a look at that thunderstorm again. If you see lightning, you count 1, 2, 3, 4, 5, 6. When you hear the thunder, that means that lightning is about 2 kilometers away. So how long did it take light to travel that distance? Only 2/3 of 1,000th of a second. Compared to the speed of sound, at these distances, light does arrive practically instantaneously. But when you're dealing with the vastness of space, distances can be measured in how long it takes light to travel. We visited the Wellesley College Observatory and spoke with Kim MacLeod, who studies some of the most distant objects that we know about in the universe, objects that are light years away.
My name is Kim MacLeod, and I'm an assistant professor here at Wellesley College in astronomy. For astronomers, it does make a big difference that light travels at a finite speed, because here on Earth, on the cosmic scale of things, the Earth is pretty small, and it doesn't take light much time to travel these distances. It looks nearly instantaneous to us. But on the scale of space, distances are very big, and so even light, which travels as fast as anything can travel, even light takes a long time to traverse these distances in space. Just to give you an example, for light to travel from the sun to us would be a little over 8 minutes. Moving out in the solar system to Saturn, it would take light an entire hour to travel from Saturn to us. So as you can see, the big distances of space mean it takes light a long time to travel them. If you want to go beyond the solar system, then it's going to be convenient if we talk about something called a light year first. If light can travel from here to Saturn in an hour, how far does light travel in 1 year? And the answer turns out to be about 10 trillion kilometers. And this distance, 10 trillion kilometers, we call a light year. Things beyond the solar system are far enough away that we like to tell about their distances in light years. So, for example, the nearest star to our own sun, the Proxima Centauri star, is a little over 4 light years away. That's its distance, means light's taking more than 4 years to get from it to us. Maybe you want to move a little bit further out towards the realm where I work in my research. We could talk about galaxies, like the Andromeda Galaxy, which is the nearest big galaxy to our own. It's so distant that it takes light 2 million years to get from it to us. Now, this has some interesting implications for astronomy, because remember, I just said it takes like 2 million years to get from Andromeda to us. That means when I see the Andromeda Galaxy through my telescope tonight, I'm actually seeing what it looked like 2 million years ago. So the finite speed of light lets us be sort of cosmic archaeologists. It lets us see what galaxies look like millions of years ago. A lot of times students have a hard time understanding that a picture that they see of a galaxy today represents the galaxy a long time ago. Maybe you can use the analogy of mail. Let's say you have a friend who's traveling through Europe and has just visited the Leaning Tower of Pisa and writes you a postcard. It says, today's Monday, and we went to the Leaning Tower of Pisa, and we had pizza, and pizza here tastes different than pizza there. And then the postcard is mailed to you. And it doesn't get there for maybe a week, maybe 10 days. And when you get the postcard says, today is Monday, we're at the tower, but your friend is not there. This represents a snapshot in time from last week. Same thing with the light from the Andromeda Galaxy. So what I study is quasars, and these are very powerful galaxies, and they are so distant that it's taken the light about 10 billion years to get from them to us. So by studying these quasars, I can learn about what the universe looked like, what galaxies look like 10 billion years ago.
We know that we can't see around corners, And we can't see what's behind us either, unless of course you're a teacher and have eyes in the back of your head. Light travels from a source of light like our sun, the stars, a light bulb, a candle flame, computer screens, fireworks, and even fireflies, directly into our eyes. But most things we see are not sources of light. We see most objects because light that originates from a light source strikes these objects and then is reflected and enters our eyes. The idea of the role of light in seeing objects is not a simple one. We visited a fourth grade class in Worcester, Massachusetts, where the students were explaining their ideas about how we see.
I drew a car and I have an eye looking at it, and these are seeing lines, but you don't like, when you're looking at something, it does, if someone's looking at you, they don't see seeing lines, it's invisible. It helps us see because if we don't have any light, then we couldn't see anything. Well, a lot of people think we can see in the dark, but all we will see is black and white, and we need like either seeing lines or something to see or like look at something.
How we see is we use light because we can't see without light. And here the sun is reflecting toward the eye, off the eye, and the eye sees by looking at the tree. And inside here, it's upside down and then reflects back out, and you see it right side up. And down here I'm seeing, the eye sees by looking at the tree with help by the sun for light. Inside the eye, it turns the picture upside down and bounces back out and sees the picture right side up.
What I drew was, for an example, I drew a fish for the picture, and the sun is reflecting on the fish because I drew a little key here. It's like, this is kind of like a web here, and like the yellow one means sun reflection, and the red one means reflection to the eye. That means the reflection is going into the eye. I wrote sun reflects on the picture, so it's reflecting off of the fish and it's going into the eye.
This is the sun, and these are light rays. The light rays are going at the tree, and then the light's bouncing off the tree. It's going into the eye like this. Then these light lines cross, making the tree look upside down at the back of the eye, which is called the retina. The retina has a nerve that's connected to the back of the brain, and the brain tells you which way the tree should be and how far it is, and it makes you see it good. And without light, you can't see anything because the light needs to bounce on an object so it can go into your eye and into the back of the brain.
The light source in this poster is the sun. Light from the sun reaches the object, in this case a fish, and some light is reflected off the fish. The reflected light enters the eye, resulting in vision. Exactly how the eye responds to the light entering it will be the focus of Workshop 4.
So we've seen that children often don't recognize that light from a source is reflected off an object and then into our eyes. But what do we mean by the term reflected? Perhaps you think of reflection as light that's reflected off a mirror or another smooth surface, like glass or a pond. That's definitely reflected light. But in fact, whenever you see an object that isn't itself a source of light, we see it because light has been reflected from it. Think about entering a very dark room in a basement. Can you see anything? No, just darkness. nothing is giving off visible light. But you've brought a flashlight with you. Let's take a look. As you shine the flashlight and move it around, the light from it allows you to see the objects in the room. Light from the flashlight is hitting objects like the toy elephant or the poster, and some of that is being reflected back to your eyes. If you see most objects because they're reflecting light, perhaps you're wondering why you don't see your reflection in that object. In the next workshop, we'll explore that question. Let's revisit the big questions we explored in this workshop. First, what is light, and what are some of the ways light behaves? We talked earlier about light as a stream of very small packets of energy called photons. We can represent these photons with ball bearings. Of course, ball bearings are made of matter, and photons are really energy. But we can use the ball bearings to represent and help us think about some of the behavior of light. We saw that light travels in straight lines. And that shadows are formed when something opaque blocks the path of light. And we began to explore how we see objects. Light from a source is reflected off an object and then into our eyes. But let's take a closer look at what's really happening when photons hit an object. When light photons hit something, they're reflected from the object to our eyes. Now we're going to think about just one of those packets of energy, one single photon, and we're representing that photon with a ball. You might think of reflection as being almost like a ball that's thrown at a wall and bounces back. But that wouldn't be quite right. According to our present understanding of light, what actually happens when a photon hits an object, it is absorbed, and then a new photon is given out by the object itself. So instead of our photon ball just hitting the wall and bouncing off, it's caught by a catcher that is actually an electron that throws a new photon back. So while we talk about reflection as though it's a simple process, what's actually happening is more complicated and much more interesting. And next time we'll explore how light behaves when it strikes different kinds of objects. Thank you for joining us today. We'll be with you each session, and I'll be able to share more with you about how I use light in my work as an astrophysicist.
See you next time. Remember to check out our website for additional information, activities, and discussions with your colleagues. The address is www.learner.org/channel/workshops/shedding-light. You may want to bookmark this address for easy access. And if you don't have access to the web, you can share your thoughts with us by email, fax, or mail. Our email address is channel@learner.org. Our fax is 617-496-7670. And finally, our address, the Annenberg CPB Channel, Smithsonian Astrophysical Observatory, 60 Garden Street, MS-82, Cambridge, Massachusetts, 02138.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.